All right, so we saw that for piecewise functions, normally at the border point where the formula for the function changes, it's quite possible that the limit would not exist. So one important type of piecewise functions is absolute value function, right? So what do you think about absolute value function? So first, let's give you a reminder about the definition of the absolute value function. Absolute value x is equal to x itself if x is bigger than or equal to 0, and minus x if x is less than 0. So absolute value of a number, if the number is already positive, for example, absolute value 5 is equal to 5 itself. So if the number is already positive, absolute value of the number is equal to the number itself. But if the number is negative, absolute value minus 5, for example, is 5. But if x is minus 5, 5 means what? 5 means minus 5, right? So many people get confused here because they think, they many times ask me, especially pre-calculus class, they say that the output of absolute value x must be always positive, a non-negative number. So how come we say minus x as the output of x, absolute value x? The answer is minus x is not necessarily a negative number. It is possible that minus x becomes a positive number. If x itself is negative, minus x becomes positive. Okay, so it's a very common confusion in all math courses that many students think that, for example, minus x is always a negative number, or minus a, for example, is always a negative number. Well, that's not true. If x is negative, minus x becomes positive. Okay, so for example, so let me write as an example that absolute value minus 5, well, we expect to get 5 as the final answer of this, but if we let's use this formula to check whether we get 5. Well, absolute value minus 5 is, if x is minus 5, I have to use the second formula here. So it becomes minus 5, and that is 5. Because the second formula implies that if x itself is negative, you have to use this formula here. So the output of absolute value x will be minus x. So if x is minus 5, the output will be minus 5, and the answer is 5. So now the example I want to say about the limit is, does limit absolute value x as x approaches to 0 exist? So how can we answer this question based on what we said so far? To check whether some limit exists or no, we have to check the right limit and left limit. So let's do that. The right limit absolute value x approaches to 0 positive. 0 positive means x is approaching to 0 from right. How much is this? Now, x approaches to 0 from right means x is bigger than 0, right? Right limit or from right means x is bigger than the number. So if x is bigger than 0, absolute value x will be replaced by x itself. So then this is limit x as x approaches to 0. And this is 0. Why? Because we said in the case of, I promised you that I'm going to tell this formally later, but I told you that to calculate limit of a function, if the function is simply a polynomial, such as a linear function or quadratic function and so on. So to calculate the limit in that case, you can just simply replace x with the number. We will state this as a theorem later, okay? But for now, just accept that to calculate the limit of a function, if the function is a polynomial, we just need to replace x with a number. We did that, replace x with 0, we get 0. Or if you don't want to use this theorem, you can also use the approach that we did in the first half of the class, where to calculate the limit, we said, okay, so x approach 0 from right. So 0 from right means like 0.1, then 0.01, 0.001. So use those x values and look at the outputs and see how the output behaves. Is it getting closer and closer to some fixed L value? If that's the case, then you have the limit. So in this case, if x is 0.1 or 0.01, 0.001, and so on, the output is also x, so the output also is 0.1, 0.01, 0.001, and so on, which is getting closer and closer to 0, so the limit is 0. Please remember that the limit is the ultimate behavior, so like the final approach of the outputs. This is the right limit. What about the left limit?
May I have your attention, please? The building
Limit absolute value x approaches to 0 from left. So from left means x is less than 0. So x less than 0 means so x less than 0 means we have to use the second formula there. So we will get limit minus x as x approaches to 0 from left. And again, it's a polynomial. We can just, to find the limit, we can replace x with a number. We get minus 0, which is 0. So what can we conclude? So we can conclude that the right limit and the left limit, they're both 0. So that means the whole limit exists and is equal to 0 as well. Okay. This limit for absolute value. So although it's a piecewise function and 0 is the border point, but still limit exists because the right limit and left limit, right limit is 0 and left limit was minus 0, which is also 0. Right limit and left limit were equal, and therefore the whole limit also exists, although absolute value x is considered as a piecewise function. And the graph of this, by the way, if you want to look at the graph, you can also answer the question based on the graph. See, this is the graph of absolute value x. And as you can see, as x gets closer and closer to 0, either from right, or from left, still in any case, the outputs are getting closer and closer to 0. So the limit exists and is equal to 0. Okay, what about, so the next example, does limit absolute value x over x approaches to 0 exists? What about this one? So we saw that in the previous example, limit absolute value x exists and is 0. What about limit absolute value x over x? Do you think still it exists or not anymore? So again, let's do the similar approach. Find the right limit and left limit. So right limit absolute value x over x approaches to 0 from right is equal to limit x over x approaches to 0 from right, right? Because again, if x is positive, x bigger than x approaching to 0 from right means x is bigger than 0. X bigger than 0 means absolute value x is equal to x itself, and x over x is 1. So this is limit 1 as x approaches to 0, which is 1. So 1 is a constant function. When you have a constant function, the output does not depend on the input. No matter what the input x is it 0 or is it 0.1, 0.2, doesn't matter. the output is always 1 when you have a constant function 1. So if the output is always 1, regardless of the input x, well, all the outputs are 1, so ultimate behavior is also 1, which means limit is 1. And similarly, the left limit absolute value x over x approaches to 0 from left. So and x is less than 0 here, so we can replace absolute value x with minus x over x approaches to 0 from left, and this is limit minus 1, which is minus 1. So right limit is 1, left limit is minus 1. So limit absolute value x over x approaches to 0 from right is not same as limit absolute value x over x approaches to 0 from left. So that means limit absolute value x over x approaches to 0 does not exist. So right limit and left limit, each of them exist, but they're not the same. So the whole limit does not exist. Now I want to ask a question. See, we saw some examples where the limit does not exist, but in all of them, the answer was because this happened because the right limit and left limit, they exist, each of them, but they were not equal. But do you think it's possible that even just a one-sided limit, for example, right limit itself does not exist? Of course, in that case, the whole limit we said still does not exist, but we haven't seen any example of that even the right-sided limit does not exist, or even just the left-sided limit does not exist. Do you think that is possible? So let me ask this question this way, that is it possible that a one-sided limit of a function does not exist? So if yes, provide an example. If no, you have to prove why it is not possible. The answer is yes, it is possible that even just the one-sided limit does not exist by itself. In all previous examples, each of the one-sided limit, whether right limit or left limit, each of them existed. But in some cases, they were equal, and in those cases, we said that the whole limit exists. In some cases, they were not equal. We said in those cases, the whole limit does not exist. But even just the one-sided limit, it is possible that it does not exist. What is the example? So the answer is yes. Example. So see example below. Example. Let's say f of x equals sine pi over 2x. Sine pi over 2x. Does the right limit at 0 exist? So I'm going to show you that the right-sided limit does not exist for this function. The answer is no. So how can I show this? So consider the following x values. let's say, see, x is going to approach 0 from right? So let's say this is 0, and then this is 0.1, and then 0.01, and so on. So if x is 0.1, how much is the output? So f of 0.1 is how much? F of 0.1 means sine pi over 2 times 0.1. 0.1 means 1 over 10. How much is this? This is sine 5 pi and sine 5 pi is 0, right? Do you remember last time I gave you a quick review about how you find sine or cosine of a number? See, we said that, you can consider the unit circle. So this is 0, this is pi over 2, pi, and then 2 pi again is here, 4 pi is also here. Each 2 pi means one full rotation of the whole unit circle. So 0, 2 pi, 4 pi, 6 pi, they're all here. So pi, 3 pi, 5 pi, these are all here. So 5 pi is here. And what is this point? This point is -1 and 0. And we said that the y coordinate shows the sine. So sine 5 pi is 0 because the y coordinate at this point is 0. Okay, now I have to remember x is approaching to 0 from right. So that means x must remain bigger than 0, but then it has to get closer and closer to 0. So right now I am at 0.1, which is same as 1 over 10, right? Now I want to get closer to 0. So if I want to get closer to 0, I can increase the denominator, right? So how about if I increase the denominator to 11? So right now it's 1 over 10. Now let's say the next step, I would consider 1 over 11. And then f of 1 over 11 means sine pi over 2 times 1 over 11. And this is sine 11 pi over 2. Sine 11 pi over 2 means 5 pi plus pi over 2. 11 pi over 2 will be here. Right? Because 11 pi over 2 means 5 pi plus pi over 2. 5 pi is here, plus pi over 2 means you will be here. And what is the y coordinate at this point? Because remember, sine means it has to be the y coordinate. Y coordinate is defined as sine. Y coordinate at this point is -1. Now let's continue. Let's say if I increase again, remember x is getting closer and closer to 0. So to do that, I can increase the denominator 1 by 1. So first it was 1 over 10, then 1 over 11, then 1 over 12. And f of 1 over 12 would be sine pi over 2 times 1 over 12. So this is sine 6 pi, which is 0. 6 pi is here. Let's continue. X equal, let's say 1 over 13. F of 1 over 13 sine pi over 2 times 1 over 13. This is sine 13 pi over 2, which is 1. 13 pi over 2 is here. Because it's 6 pi plus pi over 2, it will be here. Then let's continue. 1 over 14. You can check that f of 1 over 14 will be also 0. And then x equals 1 over 15. You can check that f of 1 over 15 will be -1. 1 over 16. Oh, sorry, you can see there. 1 over 15. F of 1 over 15 will be minus 1, and then 1 over 16. F of 1 over 16 will be again 0, and so on. So look at the output. So see, there is no pattern. I mean, there is a pattern, but the outputs do not get closer and closer to some fixed point. Look at the list of outputs. I've erased some of them, but if you are writing notes, and you can see that the outputs, we started with 0, and then it was minus 1. It was 0, 1, again, 0, minus 1, 0, 1, 0, minus 1, and so on. See, so there is a pattern, but the outputs do not get closer and closer to some fixed point. It's first 0, then minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0, and so on. So I cannot say that the outputs, for example, get closer and closer to 0, because see, alternately, yes, alternately they are 0, but alternately they are not 0. They're not getting closer to 1 either, because yes, there are 1 at every 4 of them. But then again, 0, minus 1, 0. So they don't get closer and closer to 1 either, right? So there is no number that the outputs get closer and closer to that number. And that means that the limit does not exist. Because we would say that the limit exists and is equal to L if the outputs get closer and closer to L as X get closer and closer to 8. For example, if the outputs are 4.8, then 4.9, then 4.98, 4.998, 4.99998, 4.99998, and so on, then we say that the limit is 5. But here that's not the case. The outputs are not getting closer and closer to any number. They're not getting closer and closer to 0. They're not getting closer and closer to minus 1 or 1 or anything else. So that means the limit does not exist. So since the outputs do not get closer and closer any real number, X is equal to 1 over 10, as we consider X equals 1 over 10, then 1 over 11, 1 over 12, 1 over 13. So we can conclude that limit f of x, as x approaches to 0 from right, does not exist. See? So even the one-sided limit does not exist. And of course, in particular, we can conclude that the whole limit does not exist either. Even the one-sided limit does not exist, of course, the whole limit does not exist either. Okay, so this is one type of example where one-sided limit does not exist. We have another type of scenario where even the one-sided limit does not exist. So let me say another scenario in which the one-sided limit does not exist. Basically, infinity limits. So let me start with an example. Example, determine the whether limit 1 over x as x approaches to 0 from right exists. So the function 1 over x as x approaches to 0 from right. So the very first question I want to ask here is that 1 over x, well, yes, it is a function, but 0 is not in the domain of the function. So do you think that is a problem, or is that okay? One over 0 is undefined, so 0 is not in the domain of the function. So can we still talk about the limit at 0? So if you look at the notes and things we said in the beginning of the class, we specifically mentioned that when we talk about the limit as x approaches to some a, that a value does not have to be in the domain. Of course, it's okay if it's in the domain, but does not have to be in the domain. So I can still talk about the limit as x approaches to 0, because remember, x approaches to 0 means x is getting closer and closer to 0, but it will not take 0. So the fact that 0 is not in the domain would not cause any problem, because x is just getting closer and closer to 0. Here is right limit, so x is getting closer and closer to 0, and at the same time, while it's bigger than 0, but it will not take 0 as its value. So we can talk about so what I said means that we can talk about the limit as x approaches to 0 from right, but still I haven't told you whether this limit exists or does not exist. So to answer this question, to find out whether the limit exists or does not exist, let's do what we mentioned as the process of finding the limit, informal definition of the limit, that as x gets closer and closer to 0, in this case from right, what happens to the outputs? Do they also get closer and closer to some fixed value or no? To consider the following x values. So x has to get closer and closer to 0 from right. So it has to be bigger than 0 and also at the same time close to 0. So we can start with 0.1. If x is 0.1, then f of 0.1 means 1 over 0.1. My f of x here is 1 over x. And 1 over 0.1 means 10. So the next x value that I can consider, so I want to move closer to 0. I started with 0.1. If I want to move closer to 0, then I can, the next step, I can consider 0.01. And then f of 0.01 will be 1 over 0.01, which is 100. Next step, 0.001, f of 0.001 will be 1000. And so on. So look at the outputs. So the outputs become arbitrarily large as x gets closer and closer to 0. Outputs become arbitrarily large as x approaches to 0. So we have a mathematical notation for this phenomenon, that when the outputs become arbitrarily large, then, so in this scenario, in this situation, in such a case, we write that limit of 1 over x as x approaches to 0 from right is equal to plus infinity. So this is just a notation for implying that outputs become arbitrarily large. But does the limit exist or no? So this is a little bit tricky and it could be a little bit confusing. So still, although I'm writing this notation that limit equals infinity, still we would technically say that the limit does not exist because the outputs do not get closer and closer to any fixed real number. Please note that infinity is not a number, it's not a real number. It's just a notation for implying that the outputs become arbitrarily large. So at the same time, so if limit f of x as x approaches to, let's say, a from right equals infinity, we can conclude that the values of f of x become arbitrarily large as x approaches to a from right, and we can conclude that limit f of x as x approaches to a from right does not exist. So both of these at the same time. I remember when I was a student, so this was confusing. I was always asking myself that, well, if the limit, if we are saying limit is equal to infinity, how come we say it does not exist? So this is a notation that we accept to imply that the values of f get larger and larger as x get closer and closer to a, but still there is no L value for limit. There is still no real number that the outputs get closer and closer to that real number. So still at the same time, both of these are true. It's again, accept as a little bit misleading or confusing, but if they ask you, does limit exist? You say limit does not exist. But can we say that limit is equal to infinity? Yes, because the outputs get closer and closer. The outputs become arbitrarily large as x gets closer and closer to a from right. Okay, so this is one scenario. I can also write similar scenarios to this. So it writes similarly. So for example, limit f of x as x goes to a from right equals minus infinity. So what do you think this means? So this means values of f of x become arbitrarily. Values of f of x become arbitrarily. Can I say small? Some people say small. Well, I would avoid the word small here because when you say small, it's not clear whether you mean, because for example, when you say minus infinity, what do we mean? We mean like minus 100, minus 1,000, minus 1 million, and so on, right? But when you say small, it could be interpreted as, for example, 0.01, because 0.01 is a small number, 0.001, 0.0001, and so on. Okay, so in order to avoid that confusion in the interpretation, we would not say that values of f(x) become arbitrarily small, because normally in mathematics, we're going to say small in something like, like I said, 0.1 or 0.01 and so on. But here, the number is big, like 1,000, 1 million, and so on, but it has a negative value. So minus of a big number. So let me say values of f(x) become arbitrarily large with negative sign. For example, like I said, minus 100 or minus 1,000. Means that it's as x gets closer and closer to a from right. So for example, you could consider limit 1 over limit minus 1 over x as x approaches to 0 from right. You can check that this is minus infinity. Right? So as x gets closer and closer to 0 from right, for example, 0.1. If x is 0.1, you plug it into your function, you get minus 10. If x is 0.01, you plug into a function, you get minus 100. 0.001, you plug into your function, you get minus 1,000, then minus 10,000, and so on. So then that means the limit is minus infinity. So can we still say that technically limit does not exist in this case? Yes, limit still does not exist. And at the same time, use this notation to imply that the outputs become arbitrarily large with a negative sign. So I defined for you limit f of x as x approaches to a from right equals infinity. Limit f of x approaches to a from right equals minus infinity. So similarly, we can, so in these two limits, we talked about right limits. So similarly, we can talk about left limits being equal to infinity or minus infinity. So similarly, limit f of x approaches to a from left equals infinity, and limit f of x approaches to a from left equals minus infinity can be defined. Okay, so again, this one means as x gets closer and closer to a from left, the outputs become arbitrarily large. This one means as x gets closer and closer to a from left, the outputs become arbitrarily large with a negative sign. So what about the graphs? How do the graphs look like? For example, when you say that the outputs as the inputs get closer and closer to a from right, and the outputs become arbitrarily large, so that means your function behaves this way. See, this means limit f of x as x approaches to a from right equals infinity. See, when you say the outputs become larger and larger, arbitrarily large, so remember the outputs are represented with y values, right? So when you say the outputs are very large, that means the y values are very large. So y values being very large means you are going higher and higher on your xy plane. So as x gets closer and closer to a from right, the y values become higher and higher. So the graph would look like this. So it goes higher and higher. And so it gets closer and closer to this vertical line. See, x equals a is a vertical line, right? You saw this in middle school or high school. And the outputs become higher and higher, getting closer and closer to this vertical line, but they do not touch this line. So this line is called asymptote. Asymptote means your graph gets closer and closer to this line, but it doesn't touch it. Just get closer and closer to it. This is called is here. X equals a is called a vertical asymptote of f of x. It's vertical because it's a vertical line. X equals a is a vertical line, and asymptote means the graph gets closer and closer to it, but it never touches it. It never touches it. I think around this point, it doesn't touch it around this point. Okay, so for other cases, we can also do the similar graph. For example, right limit being equal to minus infinity would look like this. Minus infinity means very low, like minus 10, minus 100, minus 1000. So y values are very low. And x is a little bit bigger than a. So to the right of your x is to the right of this vertical line, and y values become lower and lower, below and then similarly, so in this case also x equals a is called vertical asymptote. And for the other cases, for example, a from left, we said, see, this is the left limit being infinity. And this one is the left limit being minus infinity. Left limit means x is to the left of a, and the outputs are minus infinity means very large but with negative sign. So also in graphs above, x equals a is called a vertical asymptote for f of x. So in any of the four cases that we said, the line x equals a is called the vertical asymptote. I can mention as a summary that x equals a is called vertical asymptote of x. So vertical asymptote is also usually abbreviated by VA of f of x if either limit f of x approaches to a from right is infinity, or limit f of x approaches to a from right is minus infinity, or limit f of x approaches to a from left is infinity, or limit f of x approaches to a from left is minus infinity. So in any of these four cases, if one of these four conditions holds, then we say that x equals a is a vertical asymptote. So in mathematics, when you put or between few statements, means at least if one of them is at least true, then we are okay. But if there is and, then that means all of them must be true. But here is or, meaning that even if one of them is true, still we say that x equals a is a vertical asymptote. So for example, like what we mentioned earlier, x equals 0 is a vertical asymptote of f of x equals 1 over x. Why is that true? So because limit 1 over x approaches to 0 from right is infinity, and limit 1 over x approaches to 0 from left is minus infinity. And this is the graph, see? So basically, two of those four conditions that we mentioned here hold here. The right limit is infinity, means when x is to the right of 0, y values get higher and higher. And the left limit at 0 is minus infinity, means if x is to the left of 0, the y values become larger and larger with negative signs, so lower and lower. So two of those are true, and therefore x equals 0, which means y-axis, right? X equals 0 means y-axis is a vertical asymptote. So, but even if one of them is one of those four conditions holds, still we can say that we have a vertical asymptote. Okay, and let me do one example for graph sketching, which includes the concept of limits as well. So example, sketch the graph function y equals f of x such that, so first of all, you want the domain of f to be minus 3 to 3. So you want all of these conditions to be true for one function f of x. Okay, so remember sometimes I give this type of question in exams, and some people think that, okay, one function for condition 1, one function for condition 2. No, you want only one function that satisfies all the conditions that I'm going to list here. So you want domain of f to be minus 3 to 3, and you want f of minus 1 equals f of 0 equals f of 1 equals 0, and you want limit f of x as x approaches to minus 1 equals limit f of x as x approaches to 0 equals limit f of x as x approaches to 1 to be equal to 1. And you want the right limit and left limit at 2 at minus 2 from left equals limit f of x minus 2 from right, both of these to be infinity. Okay. So let's see how we can sketch the graph of this function. The answer is not unique. So there could be, you could have an answer and your friend could have an answer and both of them could be completely right, although different, right? So there is no unique answer, but as long as you sketch a graph of a function f that satisfies all of these four conditions, then the answer is acceptable. So please remember that as I told you in the exams, normally for exercises, normally either the questions deal with functions whose formulas are given or the graphs are given, or could be something like, so this one formula is not given, graph is not given, but the graph is asked. So some property of f are given and the graph is asked. You are supposed to sketch the graph yourself. So domain is -3 to 3. So domain means the x values, the set of all x values or the inputs. So we want the inputs. So let's say this is -1, -2, -3, and then here 1, 2, 3. So on the x-axis, we have to cover from -3 to 3. And what else do we want? We want f of -1 to be 0. F of -1 to be 0 means what? Means that's an x-intercept, right? F of -1 equals 0 means the y value is 0 as x equals -1. So that means you're crossing x-axis at that point at x equals -1, which means it's an x-intercept for your graph. So f of -1 equals 0. Means we are here. F of 0 equals 0 means we pass this point. F of 1 equals 0 means we pass this point, right? So at these 3 points, we cross the x-axis. We have x-intercept there, and limit at -1 is 1, and limit at so limit at -1 equals 1 means what? So see, at -1 itself, the output is 0. But when we say limit is 1, means when x is close to -1, the y value should be close to 1. So y value of 1 when x is close to -1, not because we already know that at -1 the output is 0. But if x is close to -1, the output should be close to 1. So I need to have a hole here because at -1 itself, the output is 0, but close to it, it could be close to 1. See, something like this. As x get closer and closer to -1, y values get closer and closer to 1. So it has to locally, your graph should look like this. Or it could look like this as well. Or it could look like this as well. So it could look like this. It could look like this. Right? So any of these acceptable. As I said, there is no unique answer. So it should be close to this point. Similarly, at 1, close to this point. At 0, also close to 1. So 0 also close to 1. So one hole here. And the last condition is at -2. To the left of -2 is infinity. To the right of -2 also infinity. Infinity means very high. -infinity means very low. Okay, so, and remember that domain must start from -3. So I'm going to start from -3. I could start from anywhere. I could start from here or here or here. It doesn't matter. Anywhere. So let's say I start from here, for example. Then I need to go to infinity before -2. So I started from -3, which was the first condition, which was saying domain has to start from -3. And see, these conditions are about -1, 0, and 1. But when I start from -3 and start moving, the first point that I reach or hit is -2. What should happen at -2? -2, to the left of it, the y value should be very high. To the right of it, also the y value should be very high. So left of it, y values are very high. Right of it, also y value is very high. And then I hit -1. -1, close to -1, the y values are close to 1. So close to -1, close to -1, like here, for example, or a little bit after 1 as well. See, a little bit before -1 or a little bit after -1, y value is very close to 1. But at -1 itself, the y value is 0. So there is a hole here, and then I fill it like this. And again, similarly, there you are. Also, same thing at 1, close to 1, y value close to 1. At 1 itself, y value is 0. See, all the conditions that we have are met except one of them. Because see, the domain right now is not mine. Domain, I guess I started from -3 all the way to 3. But right now at -2, the function is not defined. Because close to -2, a little bit before is infinity, a little bit after infinity. What about -2 itself? Right now, the function is undefined at -2 because I didn't define any point. But you can just put any points. For example, let's say if I put a point here, or you could put it here anywhere you like. But just one point, not two of them, because you remember, because you want to have a function, at each input, you are only allowed to have one output. You are not allowed to have two outputs for one input. So put a point here or here, wherever you want, so that the function is defined at -2 itself. Right now, before -2 and after -2 is defined. At -2 is not defined unless you put a point somewhere along this line. So let's say I put it here. But it doesn't have to be, could be anywhere. So I start from -3 before -2. So I start from -3 before -2, the limit is infinity. After -2, the limit is infinity because it's very high. Then I come down, and then at -1, the function is 0. Output 0 means on the x-axis at -1. But close to -1, a little bit before or a little bit after, the output is close to 1 because limit is 1. At -1, limit is 1, which means a little bit before and after -1, output is close to 1. At -1 itself, it's 0, which means you're on the x-axis, but a little bit before and after -1, you're close to 1. Similar thing for 0 and 1, a little bit before 0 and after 0, output is close to 1. At 0 itself, you're on the x-axis. Same thing for 1, and the graph continues until 3. So you just need to continue. There is no restriction mentioned about the value of the function at 3, right? So you could continue this way, or I don't know, you could continue from here. You could go continue this way. Let's say at 3, you could be, the output could be anything at 3, because no condition is mentioned about the output as 3. It's just mentioned that the input 3 has to be included in the domain, but it doesn't say that the output at 3 has to be which value. So that's up to you. If no condition is mentioned about some specific point, so then that's up to you. You can do whatever you want, right? Like I said, there is no unique and correct answer. There are lots of correct answers for this question. In fact, infinitely many correct answers for this question. So as long as you sketch a graph or a function that satisfies all these conditions, then that's acceptable and you get the full mark. Okay, so Yeah, so this is about the concept of the limit and the right limit, left limit, and the connection between the whole limit, right limit, left limit, and then we consider some piecewise function. Limit, when can we say limit does not exist? And we saw that even for some examples, even one-sided limit does not exist. And we also saw the limits, one scenario where the limit does not exist is that when the limit is infinity, and we define vertical asymptotes. And we gave an example that, sketching the graph function and all the concepts that we learned today, as well as some concepts we learned in pre-calculus. And last lecture, I gave a review about that, also involved in this question. And here, for example, -2. So this line is x equals -2. X equals -2 is a vertical asymptote because the limit, right and left limit, is infinity. And we sketch the graph of one such function, but as an exercise, you can try to sketch another function that has these conditions. Or as an exercise, you can change one of these conditions a little, try to sketch a function with those properties. I will make sure to include some questions of this type as well in the assignment, the additional assignment, because you have two types of assignment. One uploaded on WebWork that you should do it online, and one additional assignment that I'll upload on Moodle, and you can just do them for your own practice, but you don't have to hand in the additional ones. Additional assignment on Moodle, just you have to just submit the assignments on WebWork. But the additional assignment is important that you do it and complete it for your own practice to get prepared for the tests. And feel free to attend the office hours, because especially it's a flex course. So I think it's important that you attend the office hours to ask any questions you have from the lectures or any topics. Okay, thank you.